for the following functions. Find all points where the function's continuous. If the discontinuities are removable, show how to fix them. All right, I'm going to start with the function f of x. The x cubed minus 4x squared plus 4x over x squared minus 2x. This is a rational function, so we know this is going to have continuity at every point except where we divide by 0. So to find the discontinuities, all I need to do is figure out where x squared minus 2x is equal to 0, and that's going to be at the points 0 and 2. So our answer is going to be continuous at all points except for 0 and 2. Now, we've got to figure out whether those discontinuities were removable, and if so, how do we fix? So what I'll do is we'll factor the top and the bottom, and then we're going to notice the x's go away, the x minus 2 goes away, and I'm just left with an x minus 2. Okay, for the equation, I have to throw away 0 and 2 from the domain. Otherwise, we're looking at a different function because we're not allowed to put 0 and 2 into the original. This is the equation of a line. So I'm just going to draw the line for x minus 2. And then I'm going to punch holes where we have 0 and 2. So if you notice, these are definitely removable. So to fix them, I just got to figure out what I'm going to do. How do I plug in those points? Well, for 2, we want the y value to be 0. So I'm going to have f of 2 equal to 0. And for 0, I'm going to want to define it to be equal to minus 2. So we're going to have f of 0 equal to minus 2, f of 2 equal to 0. And that's how I plug the holes in. Another way to think of this, okay, you want continuity. That says the limit of the function at your point is equal to the actual value of the point. So I would also want to take the limits of the 2 points to see if that matches my original answers. If I take the limit as x goes to 0 of, okay, top over bottom, I can factor the x's out. When I put 0 into what's left over, I get 4 over minus 2. That gives me a minus 2, and that agrees with the way we got it through the picture. For the limit as x goes to 2, again, we can factor. We'll punch out 1 x minus 2 in the top and bottom. And then that's going to give me a 0 over 2, which is just 0. And again, that agrees with what we got from the picture. Okay, let's try another one. Try f of x equal to x squared minus 4x plus 4 over x squared minus 5x plus 6. So, again, we apply our rule for rational functions. It's going to be continuous at all points except where we're dividing by 0. So what I'll do is I'll factor, get x minus 2, x minus 3. So I know we're continuous everywhere except x equal to 2 or 3. Okay, if I try to reduce this, just to get an idea of whether we have removable or non-removable discontinuities, we see that we're going to wind up with x minus 2 over x minus 3, and I have to throw away the point at 2. So the idea here is going to be, well, when I throw away this x equal to 2, I'm going to be able to get the limit at that point as a number, and we'll do that in a little bit. But here, I'm not ever going to be able to fix this. If I put a 3 into this, I'm going to be dividing by 0. It'll be 1 over 0. No way to fix that with a limit, so that's going to be non-removable. Okay, we'll also see this in the picture. Okay, so let's do the picture to see if it agrees with what I just reasoned out. Now, to get the graph of this, you may want to go to a computer, or you may want to plot some points judiciously to see what's happening. But one great thing about calculus is that we're going to learn how to draw real pretty pictures of functions. So that'll come later. For now, we take this as a given. Okay, so let's note. We're going to have vertical asymptote at x equals 3. Okay, you plot enough points to see that these are going to happen. Horizontal asymptote at 1. And then we note we got to throw away the point at 2 because it's not going to be defined in the original function. So this is what we get. So you notice you can't fix what's happening at 3 because of the vertical asymptote. But I could plug in the hole here, so I want f of 2 to be equal to 0. Okay, we want to make sure that the limit agrees with that. If I take the limit as x goes to 2, okay, we factor like so. The x minus 2's go away, leaving me with x minus 2 over x minus 3. I put the 2 into that, I get 0 over minus 1, and I get my 0. So we can fix this point, can't fix the asymptote. To finish up, let's do a trig function. Let's do f of x equal to secant of x. Okay, secant of x is defined as 1 over cosine. So rule for trig function says going to be continuous everywhere except where you're dividing by 0. So I'm going to wind up with, I just need to find points where my cosine is equal to 0. All right, well, if I draw the graph of cosine, we know, okay, remember it starts at 0, it's going to be equal to 1, and then it's going to come down, go back up, and keep repeating. So it's going to hit its first 0 at pi halves, go down to pi, and then the next 0 is going to be at 3 pi halves. So what we see is we're going to get zeros where we're at a multiple of pi halves that's not also a multiple of pi. So the way I write that is pi halves, and then we just do plus minus multiples of pi. So we're continuous everywhere except at these points I've just written down. Okay, now note, if I draw the graph of secant, so we just flip everything over, so I'll just keep track of where the zeros go. The zeros are going to turn into vertical asymptotes. You note, these are not going to be removable discontinuities. We're going to have vertical asymptotes at each of these points, so there's nothing that we can fix.